An ideal air handling system with no heat loss or heat gain through the ducting supplies 62 degrees Fahrenheit dry bulb air at 83% RH to a conditioned space, which has a thermostat set for 71 degrees Fahrenheit dry bulb and 65% RH. The total heat load on the return air is 185,000 BTU per hour, while the outdoor air load is 44,000 BTU per hour sensible heat and 17,000 BTU per hour latent heat. If a cooling coil services the load with 25.3 GPM of flowing chilled water, the temperature drop across this coil will be most nearly what? Initial critical thought solution elements. 1. What are you solving for? The temperature drop across the coil due to the energy demand of the load. 2. What is the fundamental process? Steady flow energy and heat transfer for water, not air. 3. What are the first considerations to find the solution in connection to the fundamental process? How an air handling system and refrigeration system connect via cooling coil operations. Also, what the necessary data are for determining energy flow in a coil. 4. Are there key assumptions? That there is likely useless and misleading information in the question which must be filtered out in your analysis. That the air handling system is simple and standard with no exotic configurations. Also, that the water flowing through the coil is also standard as it relates to its heat transfer properties. Many, perhaps most, questions on the PE will contain unnecessary and even misleading information. This question is an example of such a circumstance. A tester who thinks that the PE questions should be clearly written with a direct indication of what must be solved and a simple laying out of the necessary variables will experience lost time on exam day. It isn't that the questions are poorly written. It is to challenge the clarity of your understanding by purposefully making a mess. Engineers who know their stuff and are aware that there will be misleading information to dig through will develop a good mess filter. Here is a standard and simple air handling system with the following airflow paths: return air, exhaust air, outside air, and supply air. The standard and simple placement of a cooling coil is just upstream of the supply airflow path. This should be obvious. You're not going to spend energy conditioning air which will be rejected, so it wouldn't go here. You are also not going to put it here with all the potential chaos of variables before it is mixed. Reference the NCEES Mechanical Reference Handbook, Section 9.3.1 for a more complete layout. Because the question is asking you about the actions of the coil, you could potentially consider what temperature and relative humidity changes are occurring within the airflow as it passes through it. But you are only given temperature and RH data for those 2 points. Both are downstream of the coil. You don't have any entering data. So, a simple knowledge of an air handling system will allow you to quickly throw out the temperature and RH data as unnecessary. Filter that mess out. Now, speaking of messes, the whole issue of heat losses or gains through the ducts due to fans or whatever indicates unnecessary information. Of course you have to ignore duct and fan contributions because there's absolutely no info in the question about ducts and fans anyway. You'd need data on the ducts, such as insulation, wall geometry, heat transfer, surface area, or on a fan, horsepower, efficiency, etc. There are ample indicators within the question that you are being given a mess. These messes are testing you on understanding a critical issue in HVAC. that air handling systems and refrigeration systems are connected through things like coils. It's important to understand which system you are analyzing and how the different system characteristics affect each other's operations. Do things like the temperature or relative humidity of the air flowing through an air handling system contribute to the demands placed on the refrigeration system, which pumps the chilled water through the coil? Yes, but only in certain ways. This question is actually much more about the refrigeration system than it is about the air handling system, but the wording can make it seem like you should be paying attention to the air handling system. The refrigeration system is handling the chilled water. The demand on the coil will affect the GPM flow of the chilled water. And the temperature drop across the coil is not a drop in air temperature. It is a drop in refrigerant temperature. The hugely important energy flow equation, also called the steady flow equation, will be the key to unlock the mathematical and analytical information that is actually critical in this problem. A general outline of the equation can be put this way. Heat or energy flow is equal to fluid flow times material proportionality times a change in system quality. Heat or energy flow will be something with units like BTU per hour, or HP, or kilowatts, and is often called things like load or demand. Fluid flow will be in something with units like pounds per hour, or GPM, or CFM, and it's often called things like mass flow or volumetric flow. Material proportionality will be in the most strange units of the problem, either long units or no units. Units like BTU per pounds degrees Fahrenheit or unitless coefficients, which are experimentally derived. And it's often called materials critical something or its specific something, or perhaps a coefficient or factor of something. Change in system quality will be the deltas for things like temperature, pressure, head, enthalpy, or humidity ratio. In the PE, you will be asked about this over and over again and in all sorts of permutations. You must have 4 of these energy flow equations memorized. 3 for air, 1 for water. Total heat, sensible heat, latent heat, and water. The only things that change are the value of the material proportionality and the delta of the system quality. You will see these equations come up in many other videos, but you only need to focus on the water version of the energy flow equation now. Be aware, this is tucked away in a very obscure location and topic in the NCEES Mechanical Reference Handbook, Section 9.4.5. Heat or energy flow in BTU per hour is equal to fluid flow in GPM times 500 times delta T in degrees Fahrenheit. The 500 is given as unitless, but it is the product of density in pounds per cubic foot, specific heat in BTU per pounds degrees Fahrenheit, along with a conversion from mass to volume for the flow of water. Heat is being transferred to or from the water flowing through the coil as governed by this equation. What heat? The first and most obvious indicator of what heat is found in the units given, BTU per hour. But you're given 3 types of heat: total, sensible, and latent. Total heat is the sum of sensible and latent heat. You should know this. If you don't understand this, study ASHRAE Chapter 17, Residential Cooling and Heating Load Calculations, Section 6 on Basic Relationships. Add the sensible and latent heat loads together to get the total heating load. Then, based on your knowledge of the air handling system and its relationship to the placement of the coil, add the 2 total heating loads together and you have this value. The fluid flow is the chilled water and is given in the problem as 25.3 GPM. Now, algebraically solve for the delta T, which is roughly 19.5 degrees Fahrenheit. To get good at questions like this, study ASHRAE Systems and Equipment, Chapter 13, Hydronic Heating and Cooling, Section 2.2. In the ExOverZero practice tests, do problems Test 1, 18, Test 2, 16, Test 3, 18, and Test 4, 18. These contain extremely valuable variations and alterations of the fundamental concepts used in the NCEES practice problem number 20. These problems are not just repetitions. They expand and deepen your knowledge of this particular subject within the context of practical PE-style problems.